Okay, let's get on. Can we start again? Can we start again? Okay, now I want another rule-based approach, one which is very popular in expressive languages such as first-order languages, and that is called resolution, and it is a very simple calculus, as opposed to the one we've just had a look at where you have to rewrite all your formula. So remember, we have these rewrite rules. Basically, you have in the modus ponens case, that is the one that we've seen before. If you have an implication in your data and you have the premise of the implication, then you can add conclusion to the database. So basically, you increase your data set by those rules. The one that was very useful for Davis-Putnam, the way of thinking is that if you have A or B and you have the negation of B, then you can just write A. These kind of things have already been exploited, of course, in the other calculus in Davis-Putnam. But here there is one more rule, and that's the one that you referred to, namely that if we have a clause A or B and a clause not B or C, then we can simply add an element A or C to the clause set. And we can show by truth table that these two things are indeed, that this indeed follows from this one. And now it has been proven that this a calculus where you just apply this one rule on clause normal form, namely the resolution rule, is already by itself sound and complete and terminating. Yeah. So we have now only one rule, and that is this rule. Yeah. And that is quite powerful because we now have a very simple algorithm. It can be very efficiently, effectively being implemented. And it has these nice properties, namely that it is sound, complete, and terminates. Again, resolution can only check for unsatisfiability. So all you need to do in order to prove entailment again is to do the same trick. You assume the opposite, and you show that the opposite is unsatisfiable, and then you get entailment. Yeah, so it's the same as we did with Davis-Putnam. Here again, it's a proof by contradiction. So the algorithm is again same we had with Davis-Putnam. If you want to show entailment, you transform the knowledge base in closed normal form. You transform the negation of the thing you want to show entailment for into closed normal form, and you add the two. And I have now two ways of writing this down. One time I have a knowledge base as a set, and then you add the negated formula to the set, or it is a formula itself, and then you can just do the conjunction of the two things. It's exactly the same thing. And then we have basically, if we do this closed normal form calculation, and the negation of the thing we want to show, we have a clause set of clauses, and we apply the resolution rule to the resulting clauses. And then we do that as long as we come to the situation where we have an empty clause, as it's called. And what is an empty clause? It is basically if we have a clause P, and if we have a clause non-P, then we can derive that basically. Remember, so there is nothing here. So basically what you derive is nothingness, a contradiction. The contradiction in resolution is called the empty clause. And if you find the empty clause, then you have shown that there is a contradiction, and then you have shown entailment. So the empty clause stands for unsatisfiability, because P and not P can never be true, of course. So you derive a contradiction. And if you derive the contradiction, your clause set is unsatisfiable. And if the clause set is unsatisfiable, the formula is entailed. Yeah, it's the same algorithm that we had with Davis-Putnam. The only thing is that we applied Davis-Putnam to the clause set, and then we didn't find a model. That was the unsuccess criterion here. Here we find one solution, one contradiction, and we're done. So here's the algorithm. In pseudocode, you just run a loop where you apply the resolution rule as often as you can, unless you derive the empty clause. If you empty clause, then you say there is a contradiction. And otherwise, you just add new resolvents to your clause set. There are some variants of this. So this was the rule that I showed before. If there is an L2 and a negation of L2, on literal level, if there is this contradiction, you just delete both the L and the L2 and the negation of L2 and add the rest to your set, namely L1 and L3. Yeah. And there is a very powerful one, which is the same idea as we had in Davis-Putnam with the unit clauses. And that basically, this is the one that you're really looking for if you have one clause which is just a literal meaning an atom or a negated atom. And there are some generalizations, but we leave these generalizations out. So in the simple examples that we're playing around with, we only have clauses where we do the resolution between single atoms and negated atoms. So here is the idea. Basically, this is our example from the Wumpus world again. And all you have to do now is to transform this into closed normal form. That is something we did yesterday. And when you do that, you come out with those clauses, and I write them down here. It's these three clauses. So the first one is not P21 or B11. The second one is not B11 or P12 or P21. Then we have not P12 or B11. And then we have not B11 and we have P12. Yeah. So this one was is the negation of the thing we want to prove in closed normal form, because it was very simple. It is already in closed normal form. So this is something we got out of the exercise of transforming this formula here into closed normal form, just by rewriting according to those rules in the right order. And now let's see, it's written down there, up there, so you can cheat. But how can we apply now resolution rule here? And the hint is that you should always start, if you have a unit clause, start with a unit clause. But it's a simple search process now. We just have to look for a resolution rule that we could apply between some of those clauses. So is there in these two something where we have an atom occurring once negated and once non-negated? P21. Okay, let's check P21. So we take these two, and we can derive out of those two a new clause. Yes? So it's B11 or negation of B11 or B21. P21. Oh, sorry, this one we have, yes, I got the wrong one, 2. Yeah. Okay, so we just add this to our knowledge base. So now the next step is how can we integrate those two? Is there anything? Yeah, we have B11, for example, occurring here. So then we just write P12 or P21 or non-P12. Yeah. So then we can delete this one because it has B11 and not B11, and that's always true. And I think we can also delete this one because it's always true. And we can go on. We have now done those two. We have done those two. We can also do the B11, not B11. And that gives us a contradiction here. Okay, so you see the principle. I just try to combine those into more of those clauses. And if you look at this picture, this one is the one that we have here, the B11, P12, or B11. This one is the one that we have here, and so on. And the most interesting one is when we start with the B11 here, so that's this one, plus this one on the side here, so this one, these two. What do we get? Yeah, so we have these two go. So all is left is this one, not P1, not P21. P1. But we can also do these two. So this and this gives us not P1, 2. And then these two give us the empty clause. Yeah? So basically, if you do the calculation, the full calculation, it's only this little bit in the corner that is interesting, because you can derive the not P12 from these last two clauses here, and the P12 from the remaining. With this new clause, you derive the empty clause. So basically, all you have to do, and you have to practice that a bit, is to search for which things can I combine in order to derive this empty clause thing. Yeah.
Last slide. You combine first. I don't get how it doesn't go to like just P12, because like the B11 and they're not P11, they cancel each other out.
They cancel each out within one clause. So if you remember how these clauses, what the meaning of the clauses were, it was that this is a disjunction of a conjunction of things. So here you say it's either this or this or this. And if you make this one true, then in a conjunction, that is perfect. That's what you want. So you want in a conjunction, okay, true and true and true makes things true. Problem is if you have a conjunction that says, I have something that must be true, namely that P1 is false, P12 is false. Here I say P12 must be true. So you have two clauses that contradict each other. That's why it's a problem. Not where you have a disjunction where you have the whole spectrum, that's fine. It's either this one or this one, no problem. But here it is both this one and this one, and that is impossible. Yeah? Clarify things? Okay. So what you have to do is simply take your formulae, and you will get far simpler ones than this one, because this is sort of messy if you have to do that in an exam or in a practical. You get something simple like this, and all you have to do, and that's probably a good way of thinking about it, is to write it down as a search tree. So you start out with your formulae, and you produce new clauses just by applying this rule. And what you want to do is get down to this contradiction in the end, to the empty clause. So you start out with, so these are your formulae in the knowledge base. You apply the rule to produce new ones of those, and you get smaller and smaller and smaller until you find the empty clause. Yes?
Why do you want to find empty clause?
The use of the empty clause is that if you find the empty clause, your whole knowledge base is unsatisfiable. Because basically, as you've seen in this picture, we have to fulfill a constraint that P12 must be true. That's the first assumption. And we can derive that there is another constraint, and that says that P21 must be false. Yeah? And these two constraints clash. So here we produce a global contradiction of the whole knowledge base using this resolution calculus. which is a completely different paradigm than the David Putnam one, where we tried to find a model. So we looked at all the possible combinations of things, and at the end we failed. So in one we look for a model, and here we look for a contradiction. These are the two different paradigms, and they work very well for different applications, and we're getting into that. That's a really logic issue of which representation do you want for which problem. But that's the general idea, that here you look for a contradiction where two formulae really say the opposite thing, and both have to be true. So then the empty clause stands for, this is the impossibility. Yeah?
Where the nodes with no parents are coming from?
These would be the input. So these are your nodes from the knowledge base that are given. So you start out with two, and you can always add the ones that you have already in the set to the mix.
So not R, B, and not Q are given.
So this is given, and this is given.
And then we have to derive it.
And then this one is derived from these two. This one is derived from this two, and this one is also given. Yeah. So in this case, you always add the things in the knowledge base. It's just one graphical representation that is a bit different that might help for doing this. Yeah. Just try to play around with it a bit. And as I said, you will get an easy one, a simple one, not an easy one, but a simple one in the exam, where you just have to know that all you have to do is look at your knowledge base. Do you find something that is the negation of part of the clause? And if you do that, do you come to a point where you have a clause that says A and a clause that says non-A? So in two clauses, not within one clause. In one clause, that's no problem. But if you have two different clauses that contradict themselves, then you have a problem. Or now you don't have a problem. You have the solution. You found that it's unsatisfiable. Yeah? Sorry? This is also given, yeah. So all the parents are given. So in this case, we would give you a knowledge base, not P or not Q or R, and not R, and P, and not T or Q, and T, I think is the last one. Yes. So this would be the input. Yeah, that would be the input. I think it should be visible. Yeah. So this is the input, and then you just do the resolution with these two. The way I do it usually is that I give numbers to them, 3, 4, 5, and then I get number 6, which is a resolver between 1 and 2, and that is then not Q or R. Yeah. And then I can do what is it? Not Q. So this is not P or not P or not Q. Yeah. And then I get number 7, which is number 6 plus number 3, and that gives me not Q. Yeah. So that's a different way of writing it up, which is maybe also quite intuitive.
But it just depends, like if like something is inside the knowledge base or not, because it could end at Q already, like not Q, and then Q equals empty. So it's like you can already prove it before, but it just
yeah. You try to find the empty clause as early as possible, but if you wouldn't have T, it might be that you have to exhaustively do all the combinations, and in the end not do anything. And the moment you saturate, you haven't found the empty clause, you know that you're satisfiable, but you don't find a model. Okay. So the things that I want you to remember from the logic perspective, and that is going to be also written in the worksheet for the working groups tomorrow, is that you understand the semantics of the propositional logic a bit, So when we give you a formula on a variable assignment, that you calculate whether the formula itself is true or false, that you understand the notion of entailment, that you can calculate whether a formula is entailed by another one just by looking at the models or by arguing or whatever. And then that you can apply Davis-Putnam and resolution on very simple examples. And in order to do that, not only for satisfiability, because Davis-Putnam and resolution only work for unsatisfiability or satisfiability, but also for entailment, where you need to do this pre-transformation, add the negation, do the closed normal form. If you want to show entailment, you need to do this negation thing. And for resolution, you need to have the formula in closed normal form, and in principle also for Davis-Putnam. So always transform things in closed normal form first, and then basically you're set for the exam question. Having said that, the idea is now that you have the exam questions tomorrow. The working group questions are online now, and we put the solutions tomorrow or on Friday. We put the solutions online. Over the weekend, I will publish a final version of the practice exam. So it has been open for, but it contains some mistakes. So I'll make sure that there is a practice exam beginning of the weekend. And then you have until Friday to look at the question. I really encourage you to try to answer the questions. And next Friday, we have this extra session in which we will go through all the questions of the practice exam, if that is needed, so that you are prepared for the kind of questions that you can expect in the exam. And there were some people asking me whether the deadline for the machine learning one would be strict on Friday. I don't mind if the things are in on Sunday night, if that gives you a bit of breathing space. I still would recommend you do it before, because otherwise other things get long. But it's not a disaster if it's 2 days later. Yeah, if that helps a bit. It's one of the things. It's one of the things. So you have a question, or you're stretching your arm?
No, yeah, about the machine learning bot. There was I haven't really looked at it yet, but some people told me that it doesn't work correctly, and they've tried to fix it, but it still doesn't really work.
So I got a very detailed error report from one of you, which I sent through to the developer of the system and to another Python wizard in our department. So we're working on it. It seems to be an incompatibility of different versions of Skylearn. But as I said, more competent people than me are looking at the issue right now. So we hope to be able to report on that.
Otherwise, maybe give the compatible version and then downgrade. That could also be.
No, we tried. So I think if I give you my solution, it would still not work on your computer. That's the problem. So it depends on the computers. But so just to be clear here, if you fail to have a solution on Friday or Sunday because of these issues, that doesn't mean that you will not get the points. So we will take that into account. In whatever way, I'm not sure yet how yet, but you will definitely not be punished for an incompatibility of versions for complexity of software that you cannot solve. So don't worry about it. And if you have to submit something on Friday, and if we don't solve this very quickly, then just submit. This didn't work because of this error report. This is how I would have. This is my initial idea. I couldn't check it because it didn't work. And just write down your own version that you think should work, and that's good enough then. Yeah. Make sure that you try something what you think should work, even if you can't test it. Just write it down and submit it. Yeah.
Doing that, maybe I call the topic about retail.
So if you look at the worksheets, there should be always the introduction paragraph should always tell you these are the things, the learning objectives, and those are exactly what come back in the exam. Okay, so here is the I think a problem that so regularly occurs in our field, and that is that the ethical considerations are always squeezed until the very end, before you have almost run out of time, and then you think, oh, we still also have to think about the ethics. And this is exactly what happens here. So I'm left with 20 minutes to discuss this issue. While I think it is one of the most critical issues in our field. And I want to start with a disclaimer. So I'm not an expert. I'm sort of a nitwit like you probably, most of you are as well. But so all I want to say here is we collectively, as AI researchers or students and potential researchers, and we need to be aware of the consequences of what we are doing. We also need to be aware of the moral dilemmas that we are facing. So there are different theories about ethics. Ethics has, of course, been a topic that has been researched for thousands of years, even. And one of the big differences that you see very often is the one between the moral absolutism and the radical freedom. So there is some people who say that ethics can only work because we agree on a set of rules to which we all have to adhere. That's sort of something you find in religious approaches to ethics quite often, but also atheists believe in very strong rules sometimes. And the very opposite is to turn this into the absolute radical freedom where everybody is responsible for themselves, by themselves, to make the right decisions. So that's the Sartre kind of philosophy, which you find, where the one isn't better than the other, because this radical freedom also comes with a radical freedom for responsibility. So I have to individually be responsible for all the decisions that I take. I cannot hide behind a set of rules, but I have to be able to defend all the decisions I made because they are my decisions. So I'm responsible particularly because my decisions count, not the decisions that I sort of try to follow a certain set of rules. So these are two schools, and of course there are huge debates that people can have about where does our ethics measurements come from, our ethic principles come from. The only thing I want to say here is basically be aware that there are these two different worlds, and that this is also reflected in the AI field. So this is a more of the rule-based approach, where you say, how do we deal with robots? We give the robots a certain set of rules to which they have to adhere and which they have to check whenever they do an action. So here are the sort of fictive rules, the Asimov laws about robotics. The first one is a robot may not injure a human being or through inaction allow a human being to come to harm. So that's the rule of the robot serves the human. The second rule is then a robot must obey the orders given it by a human being except where such orders would conflict with the first law. And then the third law must be a robot must protect its own existence as long as such protection does not conflict with the first or second law. So that is there have been lots of discussions about those laws, and they I think intuitively they make quite a lot of sense. I really encourage you to think about them more strongly and in more detail. This is a sort of moral absolutist approach to robot ethics, where you give the rules to which the robot has to adhere. Yes? Oh, excuse me, sorry. I see it perfectly here, so thanks. So that's the moral absolutist view on that. What we are working in a research project now is, can you build the capability of doing ethically correct or morally informed reasoning into the reasoning process of the robot itself, so that a robot takes a decision and then has to reason itself and needs to do some some ethical framework in order to make the right decisions. And maybe, probably the best is to have some kind of combination, that these are the boundaries that a robot may never cross, but that there is still some reflection in our AI that we build, so that is aware of its own responsibility in the processes when it does something in relation to human beings. Okay, so that was the part about different ways of also looking at ethics. And I must add, I'm a bit confused. I gave these lectures quite often in the past. Did I talk about the trolley dilemma in the introduction course? No. Okay, good. So who is aware of the trolley dilemma? Okay, so that's good. Have you any idea what this has to do with AI and why I'm telling you the story now, or why I want to discuss this? Yeah?
Well, if you would take into consideration that the Asimov laws would be applied to a robot, it wouldn't, like, you couldn't make a decision in this case, because either way, humans are harmed. So
Okay.
the first rule will be broken, anyways.
Okay.
Even if a human tells them to make that decision, it won't do anything. It couldn't.
Okay. So the point here was that sometimes the moral dilemmas, like the trolley dilemma, are so that they would conflict with the Asimov's law, for example, so that it was even impossible. So that's I think a very fair point. I have something far more concrete in mind, and I still think you know it all, the dilemma. So it makes sense if you would mind have a quick Menti. So I would like to know how you would react in the situation. So the choice that you are given, let's see, is that should work here. That you can save 5 people by redirecting a train or a tram or whatever, a trolley, so that it kills only 1 person. And I would like to know what you think is the decision you would take. Whether it's right or not. And the first answer, yes, it would be the right decision. The second one, it would be ethically unacceptable. Third one is I would throw a dice. And the fourth one, I do not care. Okay, anybody still on it, or are we done more or less? Okay, of course we know that there is no very clear answer to that because it is a dilemma, so there is nothing wrong or right. I might say that the don't care people should reconsider their answers, because I think it is a question that everybody should care about, whatever decision you make. I want to go not this direction, I want to go to the direction of another variant, and maybe you also know this variant, and that is the fat man's variant of the trolley dilemma. Yeah. Suppose you would have the fat man standing in the way of the trolley, and you could push the fat man on the trolley so that it would save the lives of the other 5. Yeah. So now you would not sort of switch the direction of a train, but you would actually kill someone to rescue the other 5 people. So who would still do the pushing a man on the track in order to save the lives? Okay, thanks to the 6 people who suddenly started to care. But I think this is quite impressive, that there has now been a switch in. So if we take an action where we sort of push a button or something, we change the direction of the train, it has exactly the same effect. The guy is as dead as if we had pushed him, but now it's apparently the level of responsibility changes. And I don't say, from my end, there is absolutely no moral judgment here. I want to now translate this into the domain that we're working in, and that is the domain of a self-driving car. And we face similar dilemmas. Namely, so you're the programmer, you're writing a program, and you have to make a decision in the writing of your program that if the car is crashing, is driving towards a group of 5 people, and you can only rescue these 5 people by hitting the car against the wall so that you kill the driver. Yeah, is this clear? So would you program the car in a way that it would hit the driver, kill the driver, or would you program it in a way so that it would kill the 5 people on the streets? Oh. Okay, I have one more and then I want to proceed. And that's this one. Which car would you buy? Would you buy the one that kills the 5 people or that kills yourself? Okay. So I think the asking the questions is answering the questions. That it's incredibly difficult to have a consistent ethical understanding here, and that the question in the beginning is, of course, sort of very far away. But the question about the self-driving car is very, very close. So you will maybe never explicitly asked to decide between these kind of things, because we sort of claim that machine learning will take care of all of that. So it will do the right thing, but nobody knows how it will do the right thing. So maybe we have the wheel of ignorance, that we don't know what the thing does, the car does. Does it make it better? That we build self-driving cars of which we do not know which decision it takes and on what basis it takes it. And how far do we go with this unknowing things? So suppose we have some kind of training on the basis of people in some countries. Maybe the car will hit people from other ethnicities more easily, because that was in the training set somehow hidden. So the bias of a machine learning algorithm can have incredible impact on these kind of ethical decisions. Yeah. If you don't mind, I would ask you to give me 5 more minutes. Would that be okay? I know it's lunchtime, but please give me 5 more minutes to sort of round this up. And I promise you I won't go through all the 73 slides I have left in detail, but really just give you an idea of what kind of problems we're facing and that we should look at. 5 minutes, yeah? So what I want to do now is to give you a very short overview over the kind of domains and problems that we face in our discipline. And the first one is how do we treat AIs? Because they are now sort of getting more and more intelligent on the one end, but they're also getting more and more emotional. And there have been research showing that some people find it far more difficult to pull out the plug out of a tool if it looks cuddly. So the whole way of treating AI becomes something very important and very difficult to deal with. Then we have the example that the ethic problems of what we work for now can be used to very bad avail. So there was an article this morning in The Guardian which says that the future of warfare is drones that can think. From an AI perspective, it's wonderful news that we have systems that are so smart that they can do this complex thing of fighting a war on their own. But the idea is that they are going to not kill other drones. That would be fine. But they're going to kill people somewhere on the streets. And who takes the decision of, in a conflict situation, that someone is killed or not? And what is our contribution for that? If we have written a logical algorithm that does this checking, the entailment relation is that this guy should be killed. It's all far more close than we think. This is related to the question of how do we deal with animals. So there are very many conflicting ethical questions about it. So in this movie, Apocalypse Now, there has been a cow that has been, I think, slaughtered at the end just for the purpose of the movie. And there was an outrage about it. But we slaughter cows every day, millions of them, to eat them. So the motivation for doing things plays a role in our ethics decision that we make and our moral systems that we deal with. And the more intelligent our robots and our intelligent AI gets, the more this starts to become a role. Why should a laptop with emotions not have the same rights as a cat? Or why do we have different moral systems for different types of animals and then different types of intelligence? So there's a lot of work needed here. And we have today's problems that are really, really something that we should all be involved as responsible researchers. The autonomous weapons I just named. So we are now sending our autonomous systems to war. And there has been some legal discussions about that. And the law at the moment says we need humans in the loop. But what does it mean, humans in the loop? At the moment, humans in the loop means that the algorithms have been written by people. Doesn't mean that whenever someone is killed, a human has to be asked before. No, the algorithms are the humans in the loop, which obviously is a very difficult problem and not realistic and very problematic. Privacy. It is now so that Google, Facebook have more information about all of you than the KGB and the German Stasi ever had of people. Yeah? So we have now turned into a society where we give all the information about ourselves up for free. And it's reused, it's resold, and really bad things are done with this data. And it's done by algorithms that have been designed by AI people. And the AI algorithms have done very, very bad things here by incorrect racial profiling and these kind of things. This is also a big problem that if you apply these algorithms and you don't understand them well enough, you might end up really getting the stereotypes and disadvantaging the people who are falling out of your training set or are specific in this training set. Very problematic. So part of what we're doing at the VU is to look into the question of how can we make ethics more relevant in AI. It's not only at the VU, it's the whole AI community in the Netherlands. How can we make our robots, for example, our AIs, be more aware of ethical questions and maybe also have their own ethical systems? But again, also in data science, how can we do responsible data science? Fair, accurate, confidential, transparent. And this, I think, is really part of the research in AI for the future. And that was all of it. Thanks for the 2 extra minutes.